breaking news from the edges of our solar system. The comet Tri-I-Atlas is no longer behaving like a typical comet. A few days ago, astronomers observed this interstellar visitor crossing the boundary 2 astronomical units from the Sun and starting to shine much brighter than expected. Its atmosphere expanded to half the diameter of our star. The light of the comet changed to a troubling green, and oddly, it developed a tail directed straight at the Sun, which should be impossible. As it races towards Mars at incredible speed, researchers admit they cannot explain what is happening. The countdown to perihelion has begun, and with each passing hour, this alien traveler looks less like a comet and more like a cosmic mystery demanding answers. Stay with us until the end of today's study to learn what this sensation means for everything we thought we knew, and what will happen when alien chemistry finally awakens. Part 1. It becomes larger and brighter. The numbers do not lie, even when they contradict the explanation. In mid-September 2025, astronomers observing Tri-I-Atlas noticed something troubling in their data. The brightness measurements began to rise above the predicted values, increasing from the expected 15 or 16 to astonishing 12 or 14. For those unfamiliar with the inverse logic of astronomical quantities, this represents a dramatic change. Consider it this way. The values of magnitudes go in reverse order. The smaller the number, the brighter the object. A drop of just 2 magnitudes means the object now emits 6 times more light than expected. But it was not a gradual change. It was an acceleration. The database of observations of comets, known as CABs, for those tracking these celestial wanderers, began to show data that consistently exceeded the standard rising trend expected for a warming comet. Astronomers tracking events from Earth confirmed this trend. 3. I-Atlas surpassed all models that astronomers built for its path to the Sun. The critical moment arrived when the object approached 2 astronomical units from the Sun in early to mid-September. For reference, 1 astronomical unit is the distance from Earth to our star, about 93 million miles. At 2 astronomical units, Tri-I-Atlas was still twice as far from the Sun as we are, but something fundamental had changed. The increase in brightness was not just unexpected. It was alarming in its intensity. What could have caused such a sharp spike in luminosity? The most likely explanation is related to flying ices, frozen carbon dioxide, water, and exotic compounds trapped in the core since the formation of the object around another star. As solar radiation intensifies, these materials do not simply melt. They explosively transition from solid to gas, carrying dust and debris, forming clouds that reflect sunlight back to Earth. But here is what should concern us: the rapid increase in brightness. Such events often signal instability. Comets experiencing sudden gas eruptions break apart, forming numerous objects or impressive clouds of debris. They can also quickly exhaust their volatile components, leading to a rapid dimming of brightness. The fact that the comet Tri-Atlas is brighter than predicted by models indicates that we are observing processes that astronomers do not fully understand. However, this is not a reason for panic. NASA confirmed that Tri-I-Atlas is at a safe distance, never coming closer than 1.8 astronomical units from Earth, which is almost twice the distance to our Sun. The anxiety is not linked to the threat of collision, but to the need for understanding. Perhaps we are witnessing an interstellar time capsule undergoing fundamental changes in real time, rapidly approaching the inner part of the solar system. Consider the consequences. This object formed in the debris disk around another star, possibly hundreds of light years away from us. It condensed from materials that have never felt the warmth of our Sun, never experienced the specific conditions that shaped bodies native to our cosmic environment. However, now, for the first time in its history, it faces an intense radiation environment of our inner solar system. The increase in brightness may signify the awakening of chemical processes that have remained inactive for millions or billions of years. Exotic substances, stable in the cold depths of interstellar space, may now be sublimating for the first time since the object's birth. We may be witnessing the unveiling of chemical signs from another star system, preserved in perfect condition throughout the galaxy. The situation becomes even more tense. The comet Tri-I-Atlas is approaching a series of critically important dates that will determine what astronomers can learn from this unprecedented visitor. October 3rd is the date of its closest approach to Mars, at a distance of 30 million kilometers, close enough for orbiting spacecraft to observe details invisible from Earth. By the end of October, particularly from the 29th to the 30th, the comet reaches perihelion, its closest approach to the Sun, at a distance of about 1.3 to 1.4 astronomical units. At this point, the story takes a troubling turn for earthly observers. When the three-eye atlas approaches the sun, its position in the sky will be dangerously close to the dazzling light of the star. From early October to early November, the comet enters what astronomers call superior conjunction, a period when the brightness of the sun makes observation almost impossible from the Earth's surface. This means that the peak activity of our interstellar visitor, the moment when solar heating reaches its maximum intensity and the true nature of the comet may be revealed, will largely be hidden from our view. We will have to rely on the mechanical eyes of spacecraft located throughout the solar system, especially those orbiting Mars, to witness what could become the most spectacular manifestation of interstellar chemistry in human history. A bright trend in the behavior of the object called Three Eyes of Atlas indicates that it will not pass perihelion unnoticed. Current observations suggest that the object has activated after its encounter with our sun, possibly preparing for events that could illuminate previously unseen details of its structure and composition. But will these revelations occur in the weeks when Earth's telescopes are blinded by sunlight? Data obtained in September depicts an object in a transitional state. Measured brightness exceeding predicted values suggests that the Three Eyes of Atlas is becoming something different from what it was during its long journey through interstellar space. The question is whether this transformation is normal behavior for a comet of an exotic object, or if it is something completely unprecedented in our experience with visitors from other star systems. In the coming minutes, we will explore why the coma of this object extends further than possible, why its tail points towards the sun instead of away from it, and how its recent shift to a sinister green glow may signal chemical processes not previously observed in interstellar visitors. Riddles multiply as quickly as brightness increases, but first, we need to understand what we are dealing with, because the Three Eyes of Atlas is not just a comet, it is merely the third confirmed visitor from another star system, and its behavior already proves that every interstellar object follows its own rules. Part 2. The Discovery and Classification. The story of the Three-Eyed Atlas begins on a mountain peak in Chile, where robotic eyes scan the night sky with a mechanical precision that shames human observers. On July 1st, 2025, the asteroid warning system, ATLAS, detected a faint spot of light moving against the backdrop of stars. Initially cataloged as just another insignificant body, this unremarkable object will soon change our understanding of interstellar visitors. What makes an object interstellar is not just its origin outside our solar system, but the mathematical certainty that it can never be gravitationally bound to the orbit of our sun. Three Eyes of Atlas moves along a so-called hyperbolic trajectory with such energy that having completed its path around our star, it will forever continue into infinity, never to return. Orbital mathematics is merciless in its precision. This object moves at such a speed that it cannot be captured by the gravity of our sun. The name Three Eyes tells its story. I means interstellar, and the number 3 indicates that this is only the third such object confirmed in human history. His predecessors, one Oumuamua in 2017 and two Borisov in 2019, amazed astronomers with their unique characteristics that are hard to classify. Now, the Three Eyes of Atlas continues this tradition of interstellar unpredictability. The discovery and subsequent process showed how difficult it is to catch these objects. ATLAS operates from the Rio Hurtado Observatory in the Atacama Desert of Chile as part of a global network designed to detect potentially hazardous asteroids approaching Earth. The system captures multiple images of the same area of the sky over short intervals and then uses computer algorithms to identify objects moving against the starry background. On that July night, Three Eyes of the Atlas appeared as a barely noticeable strip, hardly distinguishable among thousands of asteroids, comets, and space debris filling our inner solar system. However, the restored images taken earlier revealed the object before its official unveiling and showed that the Three Eyes of the Atlas had been hidden in astronomical databases for weeks before anyone realized their significance. This delay in recognition often occurs with interstellar objects that initially appear as asteroids before developing fuzzy comas and tails that indicate their comet-like nature. The initial assessment revealed a weak coma around the central core, hinting that the Three Eyes of the Atlas were not just a rocky asteroid. Comets develop these hazy atmospheres when solar radiation causes ice to sublimate, creating expanding shells of gas and dust. The presence of a coma so far from the sun, when the Three Eyes of the Atlas were still beyond 3 astronomical units, indicated that this object contained volatile substances capable of releasing gas even in the cold, distant corners of our solar system. As news of the discovery spread in the astronomical community, larger telescopes began to take notice of this new interstellar visitor. The Hubble Space Telescope captured detailed images in July, while the Very Large Telescope in Chile and other ground-based observatories also contributed their observations. These subsequent studies revealed an object much more complex than its initial images suggested. The size estimates of the three eyes of the atlas remain blurred, which is a common problem when studying objects that are too distant and faint for direct measurements. The Hubble update in August clarified the possibilities, indicating a core size ranging from 300 to 2.5 to 5.5 kilometers in diameter, reflecting the difficulty of separating the solid core from the surrounding coma. Uncertainty in dimensions is important as it affects calculations of mass, density, and structural stability of the object as it approaches the intense heat of the sun. Speed calculations paint a clearer picture of this unusual object. Currently, three eyes of the Atlas race through space at a speed of approximately 130,000 miles per hour, which is about 58 kilometers per second, significantly exceeding any speeds typical of objects in our solar system. In comparison, the Earth revolves around the Sun at a calm speed of 30 kilometers per second. The comet's speed will continue to increase as solar gravity accelerates its movement towards perihelion, potentially reaching 68 kilometers per second, or over 150,000 miles per hour. These speeds emphasize the alien nature of our visitor. No object formed in our solar system could naturally reach such speeds without the aid of gravitational maneuvers around massive planets. The 30th Atlas carries the kinetic trace of its interstellar origin, accumulated over millions of years of travel through the galaxy under the influence of stellar gravitational fields and the rotation of the galaxy. The rarity of confirmed interstellar visitors makes each such event valuable for science. Until 2017, astronomers only had theoretical models that helped them understand how objects might behave during interstellar travel. The object Oumuamua shattered many assumptions due to its elongated shape and mysterious non-gravitational acceleration. The object Borisov appeared more familiar for comets, but its chemical composition turned out to be unique for our solar system. Now, the 30th Atlas adds a third data point to this meager collection, and early signs indicate it will be as unique as its predecessors. The behavior of this object challenges models in new ways, especially its unexpectedly large coma and unusual evolution of brightness. Every interstellar visitor seems to carry its own physical and chemical rules, suggesting that there is much more diversity in the processes of small body formation in the galaxy than we previously assumed. The classification process involves more than just confirming interstellar status. Astronomers must also determine whether the 30th Atlas is an asteroid-like body, a comet, or something entirely different. The presence of coma strongly indicates cometary behavior, but the specific gases and dust compositions revealed through spectroscopic analysis will ultimately determine how this object formed and evolved in its native star system. This is not a local comet ejected from the Oort cloud, that distant reservoir of icy bodies that occasionally sends visitors to the inner solar system. The 30th Atlas formed around another star, condensing from materials subjected to different temperatures, pressures, and chemical conditions. Unlike anything from our cosmic neighbor, it represents a direct sampling of the processes of planet formation that occurred light years ago, possibly billions of years ago. Trajectory calculations place the 30th Atlas on a path that will provide unprecedented observation opportunities, especially during its close approach to Mars on October 3rd. This geometry is not accidental. The orbital inclination and the object's timing are favorably aligned for observations from spacecraft, just as ground telescopes will lose it due to solar glare. However, understanding what we see requires more than just knowing where the 30th Atlas came from and where it is heading. The real mystery lies in how this object behaves when it first encounters the radiation of our sun, and why its behavior differs so sharply from theoretical predictions. Part 3. Trajectory and timelines. Time is running out for the I-Atlas trio, and for the astronomers trying to understand it before it disappears in sunlight. The mathematics of orbital mechanics drew an accurate map through the inner solar system, marking critical dates that will determine what humanity can learn about our third confirmed interstellar visitor. October 3rd, 2025 will be the first key milestone. On this day, the I-Atlas trio will pass by Mars at a distance of about 30 million kilometers, which is approximately 0.1 Huntning to 0.20 astronomical units. In cosmic terms, this is considered an extremely close encounter. allowing an interstellar visitor to be within the operational zone of several spacecraft currently orbiting the red planet. The circumstances are as good as they can be, yet more irritating. Just as the I-Atlas trio approaches Mars, offering spacecraft the clearest view of the interstellar object in action, ground telescopes begin to lose the ability to track it. The rigid geometry of orbital mechanics brings the comet closer to the position of the Sun in our sky, creating observational problems that will soon become insurmountable. By the end of October, particularly from the 29th to the 30th, the I-Atlas trio reaches perihelion, its closest approach to the Sun at a distance of about 1.36 to 1.40 astronomical units. This distance places him slightly closer than the average orbital radius of Mars, exposing the interstellar visitor to solar radiation he has never experienced during his journey through the galaxy. This moment nearly coincides with the period of greatest observational difficulties from Earth. The evolution of speed tells its dramatic story. Currently, moving at tens of kilometers per second, the trio I-Atlas will reach its maximum speed near perihelion, potentially increasing to 68 kilometers per second or about 152,000 miles per hour. In comparison, Earth maintains its stable orbit around the Sun at a speed of about 30 kilometers per second. The I-Atlas trio will move more than twice as fast as our entire planet. These speeds represent not just impressive statistics, they reveal the fundamental physical laws governing interstellar motion. Unlike objects native to our solar system, which gain their speed through gravitational interactions with the Sun and planets over billions of years, the trio of I-Atlas carries kinetic energy accumulated during its journey between the stars. Every kilometer per second of speed represents vast distances traveled through interstellar space, influenced by the gravitational fields of numerous stars and the rotation of the galaxy itself. The trajectory of the approaching object, three-eyed Atlas, places it close to the plane of the ecliptic, within a relatively flat disk where most planetary orbits are located. This geometry facilitates a close encounter with Mars and will later allow a distant approach to Jupiter in the year 2026. The orbital alignment is not accidental. Objects approaching from random directions in three-dimensional space are unlikely to pass conveniently near several planets in a short period during their transit through our solar system. Safety concerns were not considered in the case of the three-eyed Atlas, despite its classification as a potentially dangerous object in the early stages of observation. The closest approach to Earth will occur at a distance of about 1.8 astronomical units, which is almost twice the distance to the Sun and far from any potential danger. NASA's confirmation of this safe distance dispelled public fears of a collision, allowing astronomers to focus on scientific opportunities rather than planetary defense issues. The real problem lies in observational geometry. From early October to early November, the three-eyed Atlas goes through a period that astronomers call superior conjunction, when its position in the sky is too close to the Sun for practical observation. The angle of solar elongation, the angular distance between the comet and the Sun as seen from Earth, falls below 30 degrees for most of this critical period. Imagine how difficult it is to spot a firefly hovering near a powerful spotlight, and you will begin to understand the observational problem. Even the most modern telescopes cannot separate the faint light of the three-eyed Atlas from the dazzling brilliance of our Sun when both objects appear close to each other in the sky. This natural limitation of astronomy on Earth means that the most active period of the comet may largely remain hidden from human observation. The timing of the conjunction creates a fundamental irony in the encounter with the three-eyed Atlas. While the solar heating reaches its maximum intensity and the comet may undergo the most dramatic changes, the astronomical community on Earth will be effectively blinded. Gas peak emissions, possible fragmentation events, and maximum tail development may occur over weeks when ground telescopes cannot function effectively. This observational gap gives exceptional importance to spacecraft in the solar system, especially those orbiting Mars. European space agencies, Mars Express, and Trace Gas Orbiter, as well as NASA's Mars Reconnaissance Orbiter and MAVEN, unexpectedly become humanity's main eyes on one of the most significant astronomical events of the decade. The timeline after perihelion offers both hope and a realistic representation of what observers can expect. Assuming that the three-eyed Atlas will remain intact after the encounter with the Sun, ground observations should resume in November or early December, when solar elongation exceeds practical limits. However, by that time, the comet will likely be rapidly fading, having exhausted a significant portion of its volatile substances during an unobserved period of maximum heating. Brightness forecasts suggest that even at its brightest, the three-eyed Atlas comet will remain an object visible only through a telescope for observers on Earth. The peak brightness ratings fluctuate between 11 and 12 values, which is too dim for the naked eye to observe, but quite accessible for amateur astronomical equipment. The absence of a spectacular show for the naked eye may disappoint casual observers, but it does not diminish the scientific value of this unprecedented interstellar encounter. The speed profile reveals another important aspect of the timeline of the three-eyed Atlas comet. As the object approaches perihelion, its speed continues to increase under the influence of solar gravitational acceleration. However, immediately after the closest approach, this same gravity begins to slow the comet as it moves away from the sun. This change in speed affects the duration of maximum heating and the time frames available for observations from Martian spacecraft. If you look beyond perihelion, trajectory calculations show that the three-eyed Atlas continues to move further into the solar system and will eventually approach Jupiter in March 2026. Although this encounter will occur at a much greater distance than a flyby past Mars, it may provide additional opportunities for observations by spacecraft as the comet begins its final exit from our solar system. The timeline creates a narrow window of opportunities that astronomy has never faced before. Unlike periodic comets that return regularly, the Three-Eye Atlas offers a unique chance to understand an object from another star system. Observational complexities, timing of connections, and opportunities for spacecraft must align perfectly for humanity to extract maximum scientific value from this cosmic visitor. As the critical dates of October approach, the question is not only what the Three-Eyed Atlas will reveal about itself, but also whether our observational capabilities are sufficient to capture these revelations. The mathematics of orbital mechanics has set a schedule, and this schedule waits for no one. Part 4. Coma. Expansion and structure. The most astonishing discovery about the Three-Eyed Atlas is not in its interstellar origin or unusual trajectory. In September 2025, NASA's Spherex telescope discovered something that contradicted all models created by astronomers for comet behavior: an extended carbon dioxide coma stretching 348,000 kilometers from the nucleus. To grasp the magnitude of this dimension, imagine this ghostly atmosphere stretching about half the diameter of our sun. The coma of the Three-Eyed Atlas has grown to encompass the entire orbit of Mercury, creating a gas and dust bubble that surpasses anything typically observed around comets in our solar system. This is not just unusual, it is unprecedented in the history of comet science. A coma forms when solar radiation heats up. The ice in the comet's core sublimates, transitioning directly from solid to gas, bypassing the liquid phase. One can imagine this as a cosmic snowman evaporating in the sun, but such an analogy does not convey the full brutality of the process. When frozen materials rapidly turn into gas, they carry away dust particles and larger fragments, creating an expanding atmosphere that can reach enormous sizes. The composition of the coma of the comet Three Eyes tells of its formation in conditions radically different from our solar system. The prevalence of carbon dioxide over water vapor indicates that this object condensed in an area where carbon dioxide could freeze more easily than hydrogen, perhaps in the distant regions of a planetary disk around another star, where temperatures remained low enough for carbon dioxide to exist in solid form, while water existed mostly as vapor. This environment, rich in carbon dioxide, hints at the chemical conditions that existed during the birth of the comet Three Eyes. Most comets in our solar system have water as the main volatile component, while carbon dioxide plays a secondary role. The inverse relationship observed in the Three Eyes indicates temperatures and pressures of formation that have no analogs among objects native to our cosmic neighborhood. However, the composition of the coma is not its only unusual characteristic. Images obtained from the Hubble telescope and ground observatories reveal a structure that challenges fundamental notions about comet behavior. Instead of a classic tail stretching away from the sun, Three Eyes displays what astronomers call an anti-tail, a stream of material that seems to point towards the sun. This structure directed at the sun is a mystery that scientists are tirelessly working to solve. Ordinary comet physics suggests that solar radiation should push gas and dust away from the sun, creating familiar tales that have inspired human imagination for millennia. However, Three Eyes seems to violate this fundamental principle, ejecting material in directions contrary to educational explanations. Hubble's observations from July 21st captured what mission scientists called forward illumination, a fan-shaped structure extending from the core towards the sun, rather than away from it. Repeated images captured by the Gemini telescope on the 27th of August showed that this unusual geometry was maintained and developed, indicating that the anti-tail is a stable feature, rather than a temporary anomalous phenomenon. The physics of anti-tail formation is related to processes more complex than simple solar radiation pressure. Large dust particles, too massive to be easily moved by solar photons, can maintain trajectories directed towards the sun if ejected from the core with sufficient initial velocity. Moreover, projection effects can make material moving in three-dimensional space appear directed towards the sun when viewed from a certain perspective on Earth. Nevertheless, theoretical models cannot explain the constancy and brightness of the opposing flow of comet Tri-Atlas. This structure appears too sharply defined and durable to be the result of simple projection effects, while the sizes of the dust particles and ejection speeds required to create such an extensive countertail exceed what is physically reasonable for a comet's nucleus. Recent analysis suggests that the countertail may result from unusual rotational states or unique surface properties of interstellar objects. A slowly rotating core can maintain temperature differences between its day and night sides, leading to the concentration of gas formation in certain directions. As an alternative, the surface composition of Comet 3A Atlas may include materials that react to solar heating in ways unfamiliar to researchers studying local comets. The rate of the coma's expansion adds another layer of mystery. Spectroscopic observations show that the gas speeds in the coma exceed typical values for comets at similar distances from the sun. This enhanced gas emission may result from the release of supervolatile compounds that remain stable only in interstellar conditions and quickly sublimate upon first exposure to significant solar heating. Measurements of the coma's temperature show additional anomalies. The gas temperatures recorded by infrared observations suggest heating mechanisms beyond simple solar absorption. Possible explanations include chemical reactions between previously separated compounds or the release of energy stored in exotic crystalline structures of ice that formed in interstellar conditions. The three-dimensional structure of the coma, reconstructed using various angles and wavelengths of light, demonstrates asymmetries indicating uneven gas emission from the surface of the nucleus. Instead of the relatively symmetrical jets typical of well-studied comets, Tri-A Atlas exhibits streams and fans of material emanating from specific regions of its nucleus. These jets suggest that there are distinct areas on the core's surface rich in volatile substances, possibly exposed due to impacts or thermal cycles during the object's interstellar journey. The gas emission template can preserve information about the environment in which the comet formed and its subsequent evolution over millions of years traveling through space. Analyzing the dust in the coma shows particle size distributions different from those found in solar system comets. The abundance of large particles necessary for the formation of the observed structure of the countertail indicates that Tri-A Atlas either formed with different ratios of dust and ice than local comets, or that its dust particles underwent modification processes during interstellar transit. The dynamics of the comet's coma expansion show temporal changes that correlate with the comet's distance from the sun, and possibly with its rotation periods. As the comet Trigas Atlas approaches perihelion, the coma continues to grow and develop, likely reaching even larger sizes due to increased solar heating. Modeling the future evolution of the coma faces unprecedented challenges. Unusual composition, geometry of the anti-tail, and increased ejection speeds require changes in standard comet physics models. Researchers are effectively developing new theoretical frameworks in real time as observations continue to reveal unexpected behaviors. These conclusions go beyond the Comet 3-eyed Atlas. If interstellar comets regularly exhibit such unusual coma characteristics, it indicates that our understanding of comet physics, primarily based on objects native to our solar system, may represent only a narrow part of possible behaviors. Every interstellar visitor can make us reconsider the fundamental assumptions about how these objects are formed and evolve. As Atlas the Three-Eyed approaches critical encounters with Mars and the Sun, the continued expansion of the coma and its structural evolution will provide important tests for competing theoretical models. The question is whether the most dramatic changes will occur during the observational gap when Earth's telescopes cannot track the comet's behavior. But the evolution of the coma is just one aspect of the transformation of the Three-Eyed Atlas as it interacts with our sun's radiation. The most visually striking change occurred in mid-September when the entire comet began to glow with a sinister green light, indicative of chemical processes unlike anything previously observed in interstellar visitors. In mid-September 2025, the Three-Eyed Atlas performed an action that caused a wave of excitement in the astronomical community. It turned green, not gradually and not unnoticed, but with a bright emerald glow that transformed this interstellar visitor from a pale spot into something that looked almost alive against the starry darkness. The change in color was not immediately noticeable to casual observers. The three eyes of Atlas are still too dim for visibility to the naked eye, But sensitive cameras mounted on telescopes around the world have begun capturing images that clearly show a green hue around the comet's core. The transformation became particularly evident in the photographs taken during the lunar eclipse on September 14th, when the shadow of the moon provided a darker sky, enhancing the contrast of the comet's new glow. The green glow tells a story written in the language of quantum mechanics and molecular chemistry. When certain molecules absorb ultraviolet light from the sun, their electrons transition to higher energy levels. When these electrons return to their ground state, they emit light at specific wavelengths, which our eyes perceive as different colors. In the case of the comet 3 Eyes of Atlas, the green glow is likely due to diatomic carbon, two bonded carbon atoms, noted in chemical notation as C2. Diatomic